Okay, so our next topic is going to be sequences. And a sequence is simply just an arrangement or a pattern or a list of numbers. And the sequence could have a very predictable pattern, or it could have a pattern that's not so predictable, but it is simply a list of numbers. And if you take a look up here, I've got three sequences. The first sequence, 1, 1, 2, 3, 5, 8, 13, 21, is a very famous sequence. It's the Fibonacci sequence, where each number, after the first two, each number is the sum of the previous two numbers. And to get to the next one, you add the previous two numbers. And to get to the next one, you add the previous two next numbers. This sequence is a list of all of the perfect squares. 1, 4, 9, 16, 25, 36. And so each perfect square, each number in the sequence, doesn't necessarily depend on the previous number. If I want the 8th term in the sequence, I don't have to know the 7th term. The last sequence is a sequence of 1, negative 1, 1, negative 1, 1, negative 1, 1, negative 1. And similarly, this sequence, I don't need to know necessarily the previous term. If I want to know the 250th term, I know the 250th term is even, and therefore it would be a negative number, where all of the odd term ones would have been positive. So again, these are just three examples of sequences that have been listed out. Now, you can also define a sequence as a generating function. For example, perhaps I want the sequence that is defined by the function n squared minus n. And when you have a sequence that is defined as a function, oftentimes the variable is n because your domain will just be the natural numbers. So starting with 1, 2, 3, 4, etc. So if I gave this and I said list out the first 5 terms of the sequence, the first term would be equivalent to what n is equal to 1. So when n is 1, we get 0. When n is 2, you get 2. When n is 3, you get 6. When n is 4, you get 12. And when n is 5, you get 20. And this right here is a sequence of numbers whose function came from n squared minus n. The advantage of this is that if I want to get the 11th term of the sequence, I don't have to list out the first 10. I could do 11 squared, which is 121 minus 11, which is 11. So 121 minus 11, I get 110. 110 is the 11th term in that sequence. Sometimes your generating function, it may or may not have these brackets on there, but perhaps your generating function negative 1 to the n times, I don't know, like n plus 1 over n plus 2. Okay, maybe I'm looking for this sequence of numbers that fits that definition. Well, this negative 1 to the end, negative 1 to the n, all that's going to do is change your sign from either positive or negative. It's going to alternate, because if n is odd, this will be negative 1. If n is even, this will be positive 1. So if I list out the first 5 terms, let n equal 1, I get 2 over 3, but it's negative, so negative 2/3. Let n equal 2, so 3/4, but it's positive. N equal 3, negative 4/5. And, functions that are defined like this, where there's an actual function or a formula, you can always find a pattern, or you usually can find a pattern. I don't even have to look at this formula. I'm noticing the numerators are going up by 1, the denominators are going up by 1, and it's changing signs. So the next one would be positive 5, 6, and then negative 6, 7. This would be my 5 terms. Okay? These are, again, these sequences can be found quite easily because there's a function for it. Okay? The last kind of sequence, or I guess the other kind of sequence, is just like the Fibonacci sequence, where it's a recursive sequence. It's based on previous terms. And so, for example, maybe I could say, well, maybe the first term of some sequence is 2. And maybe, I don't know, the second term is 3. So notice I'm calling it a sub 1, the first term of some sequence, I'm calling it 2. And a sub 2, I'm calling it its second term, because that subscript is 2. I'm saying that's 3. And then maybe I'm defining my sequence recursively. Maybe any term, any nth term, is defined by 2 times a sub n minus 1 plus a sub n minus 2. In other words, if I'm looking for the nth term, I'm going to take 2 times the term that came right before it, and I'm going to add it to the term the item that was 2 terms before it. So if I'm looking for a sub 6, if I'm looking for the 6th term in the sequence, the 6th term in the sequence would be equal to 2 times a sub 5, right? The 5th term, that's what 6 minus 1 is, 2 times a sub 5 plus a sub 4, because 6 minus 2 is 4. Here's the problem. I don't know what a sub 4 is. I don't know what a sub 5 is. I only know what a sub 1 and a sub 2 is. So if you have a sequence that's given recursively meaning that you have to know the previous term to get the next term. To get the next term, I had to know the previous term. So I'm stuck here. I have to list out a sub 3. So a sub 3 is equal to 2 times the previous term, 2 times a sub 2, which is 3, plus 2 previous terms, 2, which is a sub 1. Oh, well that's 6 plus 2, that's 8. So now that I know a sub 3, I can obtain a sub 4. A sub 4 equals 2 times the previous, so 2 times 8, plus 2 before that, so a sub 2, 3. 16 plus 3 is 19. A sub 5 would be 2 times the previous, which is 19, right? 2 times the previous, plus 1 before that one, plus 8. So that's 38 plus 8 is 46. And then now I can calculate a sub 6. So a sub 6 would be 2 times the previous, which is 46, plus 2 previous, 19. So 2 times 46 is 92. 92 plus 19 is 11, I think. 92, 11, 11. Awesome. Okay, so here would be the first 6 terms of the sequence. 2, 3, 8, 19, 46, 111. And if you would list them out, 2, 3, 8, 19, 46, 111, okay, there may not be an observable pattern. You don't just like add 1, add 5, multiply by 2. You have to know this definition. And again, this is called recursive. If you have a recursive function, you have more work to do, because to get to any term, you have to know everything that came before it. If you want to know what the 100th term of the sequence is, then you would have to know the first 99 terms.